All right, hello. It's February 15th, 2023. We're in Cohort 3 of the textbook group, and we're in our first discussion on Chapter 2 of the textbook. So, there's a lot to discuss. Chapter 2 goes hard. Before we go into the questions that people have raised, does anyone want to just share a first recollection, something that stuck with them, or a friction, or just a sentiment, or a feeling that they had when they were reading even part of Chapter 2? You can just unmute and go for it if you want to share. It's awesome that so many people added questions. There's going to be a lot to discuss. Anyone just want to give a first thought? What did they hope Chapter 2 would do? Was there any section or quote or what stood out when people were on the low road to active inference? Okay. Let us skim in a few minutes the whole chapter, and then we're going to turn to the questions and just go based upon which questions people have voted as interesting. But let's just take a quick flyby of the low road. So Chapter 2 is going to be coming on the low road. So just to get a visual reminder of what we're talking about with the high road and the low road, from figure 1.2, the low road is like the how, showing how from Bayes' theorem, which is so simple and tautological and contentless, we get a how that meets with a why, which is this imperative for persistence and self-organization, and they come together in the generative models used in active inference, which we're going to get to in Chapter 4. So the low road is going to talk about a lot of the how and some of the what, I guess, as well. Chapter 3 is going to come from the high road perspective, and Chapter 4 is where we're going to come to the heart of active inference with the generative models. Thank you, Maria. We'll get to 2.3 and then feel free to address that. Section 2.2 is perception as inference. And this section gives a little bit of an overview on how, even before the Bayesian brain was described, there was concepts of perception as inference with Helmholtz, and even further back, as actually Maria shared in livestream 43.0. And what active inference is doing is extending that inferential framework beyond perception to also include action. That is, in the title, it's active inference. It's about inference on perception and action. This is going to be operationalized with modern statistics through what is called a generative model. We're going to come back through this, so just moving rapidly. Probabilistic reasoning is described by this equation, which is, it'll be awesome, I think, as a question asked, to have this in plain language, what is being described or what is being done with Bayes' equation. An example is introduced where a person is holding either a frog or an apple in their hand, and then the object is going to either jump or not jump. The person has some prior beliefs about a priori prior beliefs how likely frogs and apples are in the world, and they have some beliefs about what is likely to do what action. An observation comes in, and then one is able to have a posterior belief or a posteriori of how likely they think the object is to be one thing or the other. They've updated their prior beliefs through observation. So like the Bayesian moment is this critical moment where a new observation comes in, and that, in the context of a likelihood model, updates the prior into a posterior. Here's an exact Bayesian inference on that scenario. And for simple settings, exact Bayesian inference is totally fine. It turns out that for larger and more challenging statistical areas, one has to use approximate Bayesian inference. But what approximate Bayesian inference approximates is exact Bayesian inference. So this is kind of like the core of what you could do if you had infinite computational power. And you can do it for simple examples. There's a discussion of probability distributions, because there's multiple probability distributions as we're dealing with probabilistic variables. People may be familiar with the Gaussian or the so-called normal distribution or bell curve. However, there are other probability distributions that cover a different space on the x-axis. That's called support, and ultimately just have different shapes. So sometimes you want to be reducing your uncertainty about a bell curve. Other times you might want to be reducing your uncertainty about other distribution families, like waiting times. There's a discussion of two kinds of surprise. There's kind of plain surprise or surprisal, which is just how surprising was that observation? And it doesn't imply any updating of the generative model or belief. It's just like taking a look at that observation alone. How surprising was it? We call that surprise, surprisal. And it's measured in information theoretic units. A gnat is like a bit, but a bit is like a 0 or 1 coin flip. A gnat is like a bit, but it's like your coin has E sides, 2.7, etc. sides. So that's surprise. Just simply how surprising is an observation. And then there's also Bayesian surprise. Bayesian surprise, also measured in gnats, is about how much the observation updates the prior into the posterior. So they're both measured in information theoretic units. Surprisal is describing how surprising an observation is with no reference to the updating. And the second notion of surprise is the Bayesian surprise, which is how much beliefs update. Expectations are described in box 2.2. Although conversationally, we might talk about, like, are you expecting it to rain tomorrow? An expectation of a distribution is not a prediction about how it'll be in the future, necessarily. Expectation is the just arithmetic mean. So it's just the center of gravity, the center of mass of a probability distribution is its expectation. Having introduced a more general Bayesian and information theoretic perspective on just inference, it's going to return to biology. So, Maria asked, how does active inference relate with biology and psychology? Was that the point of section 2.3? So does anybody want to give a thought? Like, what was section 2.3 doing, or how is optimality and Bayesian statistics related to biological inference? Either restating what they added or just adding your own angle on it. Ali, go for it.
I think section 2.3 serves as a kind of interlude between 2.2, namely perception as action, and 2.4 action, perception as inference, and 2.4 action as inference, because before dealing with the concept of action as inference, we need to be clear what kind of inference we're dealing with here. Namely, it's not just any kind of inference that's, for example, been discussed in other various literatures and statistics or in other areas, but we're dealing with some specific kinds of Bayesian inference, which is one of its main characteristic is being optimal, because to be optimal in this framework is a necessary condition for inference, because without optimality, we wouldn't have any actionable state of knowledge. So that's one of the main points of 2.3, because I believe the concept of optimality is a necessary requirement for any biological or even non-biological agent to act as a sentient agent in any kind of environment. So that optimality is a kind of, at least in this section, it's been described as a kind of requirement for any kind of sentient behavior.
Thank you. Awesome. Great way to put it as like an interlude, because biological or even the kinds of active systems that aren't necessarily biological, we want to talk about inference on perception, but also we want to talk about inference on action. And part of the unifying capacity of active inference is that perception and action are going to be in service of a common imperative, which is free energy. It's a really important note that optimality does not imply that it's adaptive. It doesn't mean the organism succeeds. It doesn't mean it even works. So it's really worth it to see what is meant by optimality. Optimality is defined in relation to a cost function that's optimized. That's the variational free energy, which is going to be related to surprise, which is why surprise was brought up as important earlier. So it's also unpacked a lot more in the neuropsychiatry context, where instead of saying, well, healthy or neurotypical people have optimal inference, and then it's suboptimal inference for those who are different in this or that way, rather, in the precision neuropsychiatry setting, we can talk about Bayesian inference being optimal. However, with different generative models, the outcomes of optimal inference are going to look different. If somebody has an 100% belief that it rains every day, then their optimal inference will lead to them believing that it rains every day. So this doesn't mean society accepts, doesn't mean the business succeeds, doesn't mean that the model works better than any other model. It is just a statement about how Bayesian inference is going to unfold. And as Ali pointed to, this is helping us move from a perceptual inference model into a subjective, subject-specific generative model of perception and action, which can be described as sentient in the sense used by Friston et al. To mean adaptive and responsive to stimuli. Figure 2.2 is going to introduce a really important distinction between the generative process and the generative model. So, the generative model is the cognitive agent. It's there, whether you think of it as they are or they have a generative model, that's like a realist angle, or we're making a generative model for a cognitive agent. That's the instrumentalist, more map territory, falling more on the map side. So generative model is a Bayesian statistical model that is being used to describe a cognitive agent. The generative process can be thought of as the niche that is the underlying process passing observations to the generative model. The niche, the generative process, can be an active inference process itself, but it doesn't have to be. So the generative process could just be an if-then. It could be any kind of logic, it can have any endogenous dynamics. However, it passes observations through the Markov blanket as sense states to the generative model, the GM. Section 2.4. The discussion to this point is common to all Bayesian brain theories. We now introduce the simple but fundamental advance offered by active inference. Alarm bells ringing. It considers action as inference. Active inference is like Bayesian brain plus pragmatic turn. Bayesian inference perspective on action. That gets unpacked a little bit more. In the next two sections, we clarify the single quantity that active inference agents minimize through perception and action is variational free energy. So, whereas a reward learning cognitive agent would be maximizing reward, an active inference agent, as modeled as the way we're going to be exploring in this textbook, they have two ways to approach a single imperative. The single imperative is variational free energy. The two ways that variational free energy can be minimized is changing your mind and changing the world. Perception and learning and action. So, first, just minimizing the discrepancy between the model and the world. At a first approximation, the common objective of perception and action can be formulated as a minimization of the discrepancy between the model and the world. Sometimes this is operationalized in terms of prediction error. So here's a more classical prediction error minimization. This is also reminiscent of like TOTE cycles, looking for deviations and then acting to resolve deviations or discrepancies between predictions of the generative model, observations coming in from the generative process. And then here are the two ways that discrepancies can be reduced. Perception, change belief. Oh, I didn't think it was raining, but it's wet. Discrepancy, alarm bells, surprise, surprisal, surprising observations. So then what can be done? Well, one can change belief so that upon the next cycle, there is no discrepancy. Or there are situations where action can be taken so that future observations are in line with the unchanged predictions. So those two pathways, perception and action, are going to come back again and again in active inference. How much should we take the idea of cycles seriously from Jonathan? Presumably, it's much more nonlinear. Yeah, that's an awesome question. Does anyone want to give a first thought on that? There's a bunch of ways to explore this. One is, although sometimes we see it as a circle, this is actually a very informal representation. Two representations or ways of thinking about it that are a bit closer to formality. One, we're going to come to in figure 4.3 and chapter 7 as well, which is when you implement this computationally, it's going to be like unrolled as a linear sequence. So one answer is computationally, you're going to unroll the ways that these variables update each other, and they still may describe nonlinear functions. So we still can get a nonlinear function being described in various places, even if it's unrolled. And then the second formal representation that helps us escape this sort of like loops situation is there's going to be not as much in this textbook, but in a lot of the recent work on Bayesian mechanics, equations are defined for these variables, circles, random variables, as flows on those partitioned variables. So in that setting, you can draw the edges about how different variables' flows influence each other, but it's actually like an unfolding flow that's just continuous across 4 different partitions. That's the particular partition. And so you don't need to draw any kind of like looping. But the action perception loop is commonly understood, and it's also a very deep topic. Ollie, go for it.
Sorry, yeah, I think for this question, that figure from Path Integrals, Strange Kinds paper might also help to illuminate this concept of cycles and the relevance of this concept to different types of particles that have been described in this paper. So yeah, I just wanted to point it out to that diagram.
Yes, here's the flows on different states, and then the diagram. Looking a little inverted, but continue. What would you like to say about it?
So basically, in this paper, they've defined 4 different types of particles. The simplest one being inert particle, which doesn't have any active states. And as we increase in terms of, complexity or increasingly more sentience behavior, we're dealing with active particles which have active states, but as opposed to strange particles which do possess the disposition to being actually sentient particles. In case of active particles and conservative particles, there isn't any hidden active states. So that's basically encompasses the different self-organizing or even non-self-organizing entities, ranging from simple rocks to brains and organisms. So I think that's a pretty good way to somehow frame all of those behaviors within that Bayesian mechanical framework.
Thank you. Everett?
I have a question of the figure 2.3.
Mm-hmm.
It looks as if there's always discrepancy, but I can also imagine that I have a perception of objects in the world, say, for example, where there isn't any discrepancy between my prediction and my sensory observation. But that is not shown by this picture, or is it?
The discrepancy value could be 0, and especially for in silico simple examples, like where the generative model is the exact same structure as the generative process, then the discrepancy can be 0. I predicted a coin flip, heads, it came up heads, no discrepancy. I don't need to change my belief. Maybe I'll strengthen my belief, and I don't need to take any further action. So discrepancy value can be 0. However, in the context of fitting a generative model that is a coarse-grained or partial representation of potentially noisy data coming in, there's always going to be a non-zero discrepancy. So that's why we're interested in relative discrepancy reduction. But there's also contrived examples where the discrepancy could be down to 0. But there are situations where whether the discrepancy is 0 or low or already as minimal as it can be, that there may be no perception change. There may also be no action change. Or you could imagine observations coming in that induce large changes in belief, high Bayesian surprise, and are associated with the agent taking action.
Thank you.
Earlier, in the case of the object jumping out of the hand or not, there was equations showing exact Bayesian inference. Plug and chug. You just push the numbers through the Bayesian equations. Yet, exact Bayesian inference supporting perception and action is computationally intractable in most cases. And they're going to describe the cases more. It can just be understood coarsely as being hard to know the total state space of what could happen, and it might require taking an integral or sums over functions that are very large or intractable. So it can be challenging to do exact Bayesian inference. And so one of the key moves in active inference, as most currently use it today, is variational inference. It will be unpacked in Chapter 4 when we talk more about the generative models. It suffices to say that performing variational Bayesian inference implies substituting the two intractable quantities, posterior probability and log model evidence. So that's what we would want to know if we had full access to information, infinite computational resources. Doable for simple problems, intractable for higher dimensional state spaces, and so on. We're going to replace those two. Posterior probability is going to be replaced with an approximate posterior called Q. And then log model evidence is going to be substituted functionally by a free energy calculation. This is called energy-based learning, broadly. It's been around for decades. Active inference does not invent the idea of using a free energy value on a Bayesian statistical learning or inference challenge. What is different is inference on action, but it is not something that was generated within the active inference community. It's existed for decades. Variational free energy, variational Bayes is used broadly and every day. Active inference uses inference on action and perception. That's what integrates that kind of perceptual signal processing element with the action selection control theoretic element. And it uses the particular partition, which is the partition of the cognitive agent from the niche, to operationalize variational inference in this kind of agent-based perception, cognition, action loop, or just scenario. So it's always important as we're learning through, and again, multiple coats of paint, but what is actually new and different in active inference? What is describing or condensing or distilling work that is totally non-contentious and has existed for decades and is being used day to day? Evidence lower bound and energy-based learning, people will find copious examples of. So that's one deflationary take, to use a Fristonism, on active inference, is doing variational Bayesian inference isn't novel. Unified imperatives for perception and action are also not necessarily novel, but using variational inference on the particular partition so that there can be a unified imperative for perception, cognition, action is when we actually get to active inference. Equation 2.5 describes variational free energy. We're going to come back to that. Figure 2.4 gives a visual representation of how variational free energy bounds surprise. So here's like what we would want to know. Here's how we can approximate or bound what we want to know. Figure 2.5 revisits that discrepancy. Yes, Everett first.
Yes, I have some difficulty with this bounding thing. Can you explain to me, yes, this figure, what is meant by free energy bounds? What does it bound?
Awesome. So I'll just read what someone else has already added, and then anyone else feel free to like raise your hand to add more. So there's something we can't actually calculate, but we can calculate something approximately. We know that whatever value we get for the approximate thing, the true value we're looking for is certainly lower than the thing we can calculate. So we want to know the organism's age. You don't have any information about them, but you do know the organism can never live to be over 10 years old. So that's an upper bound on what you believe the age of the organism to be. So surprisal, so ln is the natural log. So natural log, and you can undo and do natural logs with exponentiation. Not going to go into too much detail on that, but it's just an operation like whether when you see something ln and then parentheses, you can take it in and out. We're going to talk more about logs later. So this is what we would really want to know. How surprised should we be for a given observation? Because if we knew how truly surprised to be for any given observation, we would have access to that true underlying distribution that is controlling how surprised we should be. Like if you don't know the range in temperature, you don't know how surprised to be for different observations. If you knew the underlying temperature distribution, you would know exactly how surprised to be with different thermometer readings. What energy-based learning does, again, this is not an active inference-ism. This is energy-based learning or evidence lower bound used broadly in Bayesian statistics, is it constructs an approximatable functional, which is a function of a function, an approximatable functional free energy, variational free energy, equation 2.5, that's a function of our approximation, which is a function, that's why f is a functional, and data. So instead of trying to find the absolute underlying surprise, how surprised we should be by a data point, which would entail knowing the true distribution, we're going to construct this functional variational free energy that's a function of q, our approximation, and y, the data. And then this is a KL divergence. The double line, what is on both of the sides of the double line is what is being divergence minimized. We're trying to minimize the divergence between our approximation and the true distribution conditioned on data. This is guaranteed to be an upper bound. It's always higher than the surprise. And then by doing divergence minimization with KL divergence, it's possible to push that upper bound lower. So it's like, here's how much the bank account actually has. Okay, I know it's less than 1 billion because there's not that many of this token in the world. Is it less than 1,000? Is it less than 5? So it's like, as you push the upper bound down, you're able, this can be approximated well. Again, whether your startup works or whether the organism lives or whether the model's adaptive or whether it's better than any other model anyone else could ever think of, that's not this question. This is saying you can generate a derivative, not in terms of like a rate of change, but like a sort of corollary value based around data and our approximation that's always higher than surprise. So surprise was brought in early in the chapter as a key imperative to surprise minimize. But then that's intractable. So we have an approximatable, tractable form. And that's what energy-based learning is, and it's not invented in active inference. But what is a little novel and different is doing energy-based learning, Bayesian variational inference, on action. We revisit in 2.5 figure free energy, and instead of it being discrepancy here, which is kind of like a prediction error minimization, that's like the TOTE, like, is there a discrepancy? Reduce the discrepancy. Well, discrepancy between the predictions and the observations, when you think discrepancy, you're thinking like, it's going to be like, I predicted a 7, I got a 9, the difference was 2. That would be prediction error. Free energy is doing energy-based learning. And so it's like a discrepancy, because if the data coming in were exactly what was predicted, this divergence would be 0. And this term would basically kind of functionally do what you would think a prediction error would do in the situation where the prediction matches the observation. But it turns out to also extend in a few other ways. But the reason why they showed the discrepancy first in 2.3, and then you can change perception or change your action selection, and then prediction, observation come together, calculate a discrepancy, and then decisions are made. Cognitive decisions, perception, or like embodied decisions in action that change the actual generative process. And then in 2.5, that gets built out a little bit beyond just prediction error type discrepancies, like there's a 4-inch discrepancy between these two things, into an information theoretic or a statistical quantity. That's variational free energy, F. Section 2.7 talks about expected free energy and planning as inference. You can't talk about variational free energy on data points that haven't come in yet, because they're future observations. And so expected free energy, G, is similar, and it's explored in 2.8. It's similar in certain ways, but importantly, and like we return to this chapter after chapter, so no worries how much of these equations look fluent to you right now. One thing is these equations have natural language representations that people can also improve, but especially like 2.5 for F, you can read it and see the active inference ontology terms being used rather than variables. And then in 2.6, it's some part of it is written. But like these are the kinds of augmentations that are always very welcome for people to make, because they help us understand. Expected free energy is like variational free energy, but whereas variational free energy is real time and it's crunching our approximation with the incoming data, expected free energy is calculated over policies, which are sequences of action, and it is going to be dealing with observations that haven't yet come in. So this is where we get to policy selection in active inference by thinking about expected free energy, which is like a prospective, talking about the expected free energy for different possible policies, which are sequences of actions. There's some more discussion about special cases. Expected free energy, when certain terms are basically zeroed out, expected free energy becomes resembling other equations. So this is like a common technique in math. You have some equation, and then like you can generalize it. And then a special case of the general form is this. And then another special case might be that. So, for example, we'll come back next week or in the future to what exactly the pieces are representing. But one can imagine that if pragmatic value was irrelevant, then G would reflect information gain of different policies. If information gain were irrelevant, like it were a totally discovered situation, then G would reflect purely pragmatic value. So G is like a generalization, it's a unified imperative, under which certain special cases resemble variously information maximizing principles or utility maximizing principles. Jonathan, is there any equivalent to discounting as in an RL context? Do you want to unpack what you mean there by discounting? But then, yes, there's definitely some angles on that.
Yeah, sure. So in a reinforcement learning context, there's a clear aim, which is to maximize the expected future returns. But generally that's done in a discounted way. And so the agent is trying to maximize the discounted expected future returns such that rewards that it gets in the future are essentially worth less than rewards that it gets in the near term. So I know that there isn't the same kind of idea of rewards as there is in reinforcement learning in an active inference context, but I'm interested to know whether there is any sort of idea of discounting that states further into the future are somehow less important than states in the moment.
Yes, here's a I'll add that question, and then add in the one Bristol paper. It turns out that yes, it's possible to get temporally discounted type behavior. So like a simple way to think about that would be if the pragmatic drive were urgent, then you would see small pragmatic gain being approached at the loss of future gain. Short time horizon models and urgent desire drive. Whereas under longer time horizons, longer time preferences, then you see the kind of behavior that in utility-driven decision-making is associated with what is called temporal discounting. So the phenomena, the cognitive behavioral phenomena exists and can be recapitulated, but it is not generated with the same way that it is in other places.
Sure. Thank you.
2.9 is the end of the low road. Variational free energy, real-time unfolding, F of Q and Y. Variational free energy, our approximate posterior Q, that's the one we control. Y, data, just like a regression. Y equals mx plus b. Q and Y, discrepancy, except it's a variational free energy. It's real time. Expected free energy, G of pi. G is a function of policies. And we're going to go into that more. But it is regarding observations that haven't come in yet. So it has a different structure, but some rhyming with variational free energy. What do they achieve together? Where did we get at the end of the low road? So, we started with Bayes' theorem. Generative model could be the thing jumping out of the hand. Perception is inference. That goes back to Helmholtz, but as Livestream 43 unpacks, this has been understood broadly across the world for thousands of years. Predictive coding helps operationalize perception as inference because it's like top-down predictions, bottom-up sensory information. That's why we don't perceive our blind spot. To bring in action, we have to talk about perception as inference because we do care about observations, but we have to talk about observations that haven't actually happened yet. And we have to talk about how our actions influence which observations are likely to occur. Perception and action as inference together make up the Bayesian brain, which is like some people, it means the brain does Bayesian computation. That's a realist take. The instrumentalist take would be we use Bayesian statistics to study the brain. And where exact Bayes is intractable, we can use variational Bayes, energy-based learning. That's the endpoint of the low road into active inference. Summary: active inference is a theory of how living artifacts underwrite their existence by minimizing surprise. That's what we would truly want to know. Surprise. If you knew how surprised to be, you would have had to have known the actual underlying distribution. So we usually can't do that. So we have a tractable proxy to surprise, variational free energy. So just like we'd want to reduce our surprise because that would reflect having the most optimally trained but not overfit belief, we want to minimize a proxy that we know is an upper bound. So by minimizing the upper bound, we're getting closer and closer to what we really want to approximate. The two ways to do that are perception and action. They motivated this from a very first principles perspective, and then extended what is often left only in the realm of perception into the domain of action. More discussion. Surprise is a construct of information theory. It's not necessarily equivalent to folk psychology. And this comes up again and again. We see it in the ontology for like half of the words. These are words that are used broadly. Perception, action, belief, surprise. And sometimes they're perfectly overlapping with formal definitions. Other times there's a little bit of a divergence. And they close. Perception, action, minimize variational free energy in complementary ways. That's real time. Active inference also minimizes expected free energy prospectively. This completes our journey along the low road. In chapter 3, we travel the high road, which reaches the same conclusion on the basis of first principles and self-organization. So we started from, we have a Bayesian model. We didn't start from organisms need to exist. But it turns out by connecting surprisal to self-organization, or really just persistent repeated measurement, we're going to get to the same place. All right, in our 5 remaining minutes, just next week, we're going to return to the questions. But I hope that it's useful to also just walk through it, because definitely it takes like multiple readings and interrogatings, and there's things that like you'd want to know in chapter 2 that are going to come up later or come up elsewhere in other papers. There's just no single road or path, let alone one that would be appropriate for all learners and their preferences. So hopefully it was useful to like look over it and see it that way. Next week, we're going to return a lot to the questions. So if anybody wants to do addition of questions, it's always great. You can jump into the answers in discourse, as I see many do, and add things. You can upvote what is interesting. You can enrich what people have written by just replacing where they use a plain text with something that you know could be tagged, just like that. So there's all kinds of ways that, like, wherever chapter 2 is sitting with you now, either by generating new questions in discourse, you can add notes on chapter 2 here, and then also in the math group, which we haven't been super active on, we've done some laying out of just the mathematical skeleton of chapter 2 as an example of how that could be done. So, but in our closing minutes, just if we can have any closing thoughts. Okay, just anyone can raise their hand, but so in relation to the temporal discounting in reinforcement learning, Ollie also wrote, reinforcement learning models opposed to ActInf are not applicable to perceptual tasks that do not involve rewards or show significantly variable behavior. So there's a lot there. In situations where pragmatic value isn't a key imperative, even if that's just a subtask, like eye saccading is driven by information gain. Yes, our eyes dwell on what might be seen as rewarding, but it's information gain that is the imperative for the eye saccading. And so where pragmatic value or reward or utility functions are either non-existent or flat, reinforcement has a hard time, and that leads to all these contrived reinforcement bonuses and novelties. Oh, maybe we'll pay him for this and we'll do that. And significantly, learning that reward function is very difficult. And learning that reward function, especially in like a partially observable or dynamic or volatile environment, ultimately you need to reward the learning anyway. So then you end up coercing what we would just call epistemic value into a reward learning framework. So why not just have a generalization of reward learning where in fully observed situations, pragmatic value can be unabashedly pursued, but in partially observable environments, or where the generative model is a simplified or coarse graining structure relative generative process, why not just authentically pursue the epistemic value, which is what you can do with G, but can only be done in a contrived or an ad hoc way if you have reward as your unified imperative. That's not to say reinforcement learning models are not effective, that, again, that the agent can't play chess or that the startup wouldn't work. It's just to be clear that the adequacy of a model in the world is an empirical question. And especially in a textbook, the points are often being made in principle. Great. Well, again, thanks for all these questions. I hope that we can rejoin next week with some thoughts and resources and other questions added in. There's just going to be a lot of fun ways to take these different questions, and we'll come back to them. So, thank you, everyone. And if you want, in the following hour, you can come to the Discord, and we're just going to continue just talking in chilling about education. So thank you and farewell.